Well, now we are going to discuss what happens when asteroids hit. And Rusty, you mentioned earlier actually that your colleagues on Apollo had a very good view of what happens when asteroids hit because we can see the surface of the moon. So can you contrast the two, the Earth and the moon?
Yeah, you fly around the moon and you see millions of asteroid craters, and that's really, in some sense, a better indicator than looking at the Earth in terms of understanding the shooting gallery, that we're part of as we go around the sun. People don't see that, of course, here on the Earth, and the reason partly is because Mother Earth protects us. Gaia, or Mother Earth, really takes care of us, both in the form of an atmosphere which really protects us from the smaller asteroids as they come in. Unless something is about the size of a 3-bedroom house, it's not going to make it to the ground. It'll burn up in the atmosphere. If it's fairly big, like 4 years ago at Chelyabinsk, that was about a 20-meter diameter object, and that one came in, didn't quite hurt anybody, didn't kill anybody. It blew up in the atmosphere and created a shock wave. But if it gets bigger than about a 3-bedroom house or so, then you're going to find serious damage on the ground. If it hits over water, it would have to be a good bit bigger to cause a tsunami. But the tsunamis are actually quite dangerous, and a large asteroid hitting in the ocean would create a lot of havoc around the borders of that water body. Water is very efficient at transmitting the energy of the impact long distances, even more than if it's an explosion in air. But there are the millions of craters that we see on the moon is the best indication to people that we're talking about a reality here.
Yeah, and actually most of those craters, Patrick, were created, a lot of them, during the late heavy bombardment. So in terms of the history, because if you look at the moon, you think it's remarkable that we've survived this long, actually. Yeah,
but we have a very short period compared to the age of the Earth. We need to remember. In fact, it's thanks to the craters on the moon that we could estimate that the current impact flux in the inner solar system is on average constant. Now we have the big basins, and thanks to the Apollo mission, which could date this basin, and there seems to have been an intensity in the impact flux about 3.9 billion years ago. We call that the late heavy bombardment because it didn't start at the origin of the solar system, or just when the Earth was formed, but it took a little time, about 700 million years, before suddenly there was a spike in the impact flux, which made these lunar basins. And therefore, it was difficult to understand how this could happen. It turns out that these are people in my team in Nice who generated the model, which is now the mostly recognized, which explains the LHB. It's called the Nice model, which if you read in English would be the nice model, so necessarily it's correct. And basically it explains the architecture, the current architecture of the solar system. So he explained why we have these asteroids sharing the same orbit of Jupiter. It explained also the small elongation of the orbit of Jupiter and Saturn, and it explained the late heavy bombardment. And the reason is that when the solar system formed and the giant planets were formed, they were surrounded by a disk of planets behind, which are now the Kuiper belt, the cometary belt. And the perturbation of this protoplanetary disk on the planet themselves took about 700 million years to build up. And that put the planet in a very unstable zone, which made them migrate. And by migrating, a lot of material went into the solar system, in the inner solar system, and generated this spike in the impact flux. But afterwards, once that was done, of course, the solar system became stable, and we entered the current era where we have all these small craters on the moon that tell us that we have a constant generation of near-Earth asteroids and impactors. The interesting thing is that most of them come from the main belt, the main asteroid belt. They have an average lifetime of a few million years. So you would say, how can it be that they live short before ending into the sun or a planet, and still we have a constant rate since 3.9 billion years? Well, it's because meantime in the main belt, you have collision fragments which are created, enter in unstable zone, and they are sent to the Earth crossing zone. So while some of them evolve in the Earth crossing zone and then die, Some of them are generated again in the main belt, and we have this mechanism of death and natality which compensate.
Julia, given that these asteroids are flying around the solar system and crossing the Earth's orbit, have we seen any hit planets other than the Earth?
Well, we did. We were so lucky to see the comet Shoemaker-Levy 9 impacting on Jupiter, actually, back in 1994, I think. And that was an extraordinary experience. We were actually watching an impact live, I mean, while it was happening. And we also see some impact flashes on the moon. And after the impacts, after these flashes, we can actually see new and fresh craters on the surface of the moon. So we are watching them constantly.
And that was a large impact. That was a large object, wasn't it? Can you give us some sense?
I think it was already broken into pieces before impacting. Correct me if I'm wrong. So each of the pieces was about 4 kilometers, from 2 to 4 kilometers. So that was a big one, yeah.
But they made scars bigger than the Earth when they hit Jupiter.
Yeah.
I mean, incredible energy.
So in terms of the Earth, just to set the scene, if a 4 kilometre diameter comet hit the Earth, what are we talking about there?
Yeah, that's the equivalent of a dinosaur killer.
Yeah.
Because the comets generally are travelling fast.
Control-Alt-Delete.
Yeah, absolutely. Resets.
There will be a lot of moves.
Yeah.
It may not be an extinction event, but it would wipe out civilization as we know it.
For sure.
Well, I mean, Rusty mentioned actually that to an extent our atmosphere protects us, certainly from the smaller ones. What do we know precisely about the impacts deflecting off the atmosphere, the angles, the modelling of the atmosphere? Do we know a lot about that?
Well, I spent a lot of time modeling that, and I've modeled the Tunguska event, the 1908 event that was on June 30th, 109 years ago today, and also the Chelyabinsk event that happened in 2013 that was captured on many dashboard and phone cameras, very well documented. And it turns out to be a very complex process. And in order to make a predictive model, you really have to know the details of the strength and the density of the impacting object. And of course, we didn't know anything about those. We didn't know they even existed until they hit the atmosphere. So we can infer something about how strong they were and how dense they were after the fact, but making a prediction, unless it's extremely well characterized, perhaps even with a rendezvous mission, beyond just Earth-based telescopic characterization, we're really not going to know at what altitude it explodes, and in some cases whether or not it'll even reach the ground.
But you can calculate that, given you know the orbit and the form of the object.
You can calculate where it would hit the ground if the atmosphere didn't exist. But for the smallish asteroids, the Tunguska size, which we think was 40 or 50 meters, or the Chelyabinsk size, which was about 20 meters, a little less than 20 meters, we really don't know how deep it would get before it explodes, because we didn't even know the shape of those. And without that information, we really don't know how long it would hold together until the pressure builds up. And the pressure may actually cause it to stay together longer than, if it's in one orientation versus another orientation, where it may start to fall apart and ablate and then explode.
I think one thing which is important is to realize that these processes are very complex, and they are in an extreme regime. So it's very difficult. We cannot reproduce in the lab the entry in the atmosphere of an object. And in fact, I'm doing the impact simulation of impact and crater formation. Mark is among the only ones who is able to do the entry in the atmosphere. So that's why we need this kind of expertise, because there are not that many people that do this kind of job. For the impact process, fortunately, we have bomb experiments that help us to calibrate the models, at least on Earth. We hope the IDA mission will fly so that we can calibrate with a real impact on an asteroid. And this turned out to be also important, because the way we estimate the age of surfaces in the solar system is by counting the craters and estimating the impact flux that generated these craters. But in order to get an age from that, you need a relation between the size of the impactor and the size of the crater. And this relies on our understanding of this physics. And the same, if you want to know now for the risk whether you have a 30-meter object coming out of you, what do you do? Whether it will hit the ground or what will be the effect in the atmosphere, you need this kind of modeling, and we can only rely on them. So that's why I push for continuing this kind of job. It's very important.
And in terms of where the object breaks up or whether it reaches the ground, what do we know about the different effects that an impact would have, if it's a high altitude breakup or a ground impact?
Well, there's actually an altitude where it can explode that will maximize the amount of energy or the amount of damage it does on the ground. Chelyabinsk exploded higher, significantly higher than that maximum optimal height of burst. If it had exploded much closer to the ground, it would have done a lot more damage. It probably would have, there would have been fatalities on the ground. As it turns out, by good fortune, there weren't any. But if it had come in at a much steeper angle, it would have gone through more atmosphere and exploded closer to the ground. It most certainly would have been more damaging. Tunguska, on the other hand, was bigger, and it did explode very close to this optimal height of burst that maximized the area over which there was damage, and that's why trees were blown down over such a large area.
So it seems, Rusty, as though if we did detect a threatening asteroid, there's a lot of characterization that has to be done before you can work out what the correct strategy is to deflect it or minimize the damage.
Yeah, there are, I mean, if you think about the practicality of an asteroid coming in and saying something to the people, what do you do? Do you get into your desk? Do you do the old duck and cover thing that were done in nuclear days?
Is that going to help?
Or do you get in your basement? Or do you simply not go near the windows if you see a bright flash? Or do you have to evacuate the city, let's say? And if you evacuate, which direction do you go? So all of these things depend upon the prior knowledge that we have before the impact of that object. And one thing that people need to understand is that there's a fair amount of uncertainty in our knowledge, and will be a fair amount of uncertainty. For example, the size of these asteroids we estimate based upon how bright they are. Well, how bright they are depends on how reflective, of course, they are. And it turns out that asteroids, a lot of asteroids, are about the color or the brightness of a briquette of charcoal. So, I mean, you're talking about something that's really dark. So we're not going to have a lot of knowledge before necessarily. Therefore, I think in spite of wanting to know a lot, we're going to have to be conservative in terms of our public defense and say we're going to assume it's bigger than it might be, rather than smaller.
I wanted to ask Alan actually about the observational astronomy, the practice of characterising these things by essentially looking at them through telescopes. How difficult is that?
Well,
Rusty's referred to it.
As Rusty said, when we first find these asteroids, they're a dot of light, and we don't know if that's a large dark object coming towards us or a small bright object that reflects a lot of light. So the first thing you want to know is the size. Now, there's a few ways of doing that, and one of the most successful telescopes at the moment is in space. It's called the NEOWISE mission. It's operated by NASA, and it's actually doing a great job in measuring the sizes of these objects by measuring their infrared light. In optical light, we can't do it alone. We need the infrared light to really measure the heat given off, strangely enough, and that gives us the size. Another great facility are the Arecibo and Goldstone antennae, because when an object is close enough, they can be resolved by radar, and that directly gives you the size of the object. And it can reveal other things as well. For example, we know from the radar studies that about 20% of near-Earth asteroids aren't just alone, they're binaries. You've got more than one asteroid there. Sometimes it's just a little moonlet, a little asteroid moon going around the main asteroid, just like asteroid Didymos that Patrick showed earlier today. Sometimes they can be almost equal size, and we can see the evidence of that on Earth. If you go to Canada, you can visit the Clearwater Lakes, 2 asteroid craters side by side, almost exactly the same size, and that's evidence that sometimes the Earth doesn't just get hit once, it gets hit twice at the same time.
Very binary. We have a question, I think. Sabini's got a question on the Twitter wall.
We do have a question, and it's a short one, but I think it's relevant to this distinguished panel. And the question is, can life survive on an asteroid?
The short answer, no. You know, we are lucky actually because on Earth we have a magnetic field that protects us from the heavy, highly energetic particles from the sun. And once we go out of it, we don't live very long. And on an asteroid, of course, because it is a very small size, there is no atmosphere, and there is no magnetic field. So life cannot survive on an asteroid. But we can have organic materials which could tell us whether they have the same properties of what we think is the structure of organic material that generated life on Earth. And the only way to find out is to go there, get a sample, and return it in the lab, like OSIRIS-REx and Hayabusa 2 will do, because you cannot do it in situ. You need a precision in the measurements that you can only have in the lab.
Mark wanted to. I was going to say that you should, because there was the controversy a while ago. The Murchison meteorite was there was a suggestion that there might be hints of life on that. I know that's very controversial and probably gone on.
Amino acids, the building blocks.
I don't really want to contradict Patrick, but if she's an astronaut and she is in a life support system, she can survive on an asteroid.
Okay. We could send life there, but we don't.
But you know, it's important. The problem of amino acid, I remember there was the discovery that you could make them in the lab. And they were thinking, oh, I think it's array, or I don't want to say mistake. And they said, okay, now we know how to form life. And then we realized that amino acids are everywhere in the universe. We found a lot of amino acids. So it's not enough to have amino acid to say, okay, this is life. Life needs something that can reproduce on its own image. I mean, there is a clear definition, and this definition cannot hold on an asteroid because there is no way to be protected from things that break basically the molecule that could form life.
Julia, did you want to come
Well, regarding the size and the uncertainties that we have, I just wanted to point out that studying the composition, although it's very limited, might help to constrain a little bit these uncertainties, to reduce them, and that will tell us if it's if this asteroid reflects more or less amount of light. So that helps to reduce the uncertainties on the size, for example.
Yeah, just point out that we have had a couple of predicted impacts of small asteroids onto the Earth in the history of our surveillance of the skies. And the first time that occurred, back in 2008, we were successful in obtaining a spectrum of the asteroid. And members of my team out in La Palma, Henry Shea and Sam Duddy, got a spectrum of it just 4 hours before it entered the Earth's atmosphere. And the interesting thing was that the spectrum didn't look anything like what we expected. It gave us, and it just showed us that we can't have too many assumptions, as you were saying, about what's coming at us.
Well, in terms of the technology, all through the day we're talking about the technology, and I suppose focusing on the spacecraft in a sense. But how much do we need to improve our knowledge of what these things are made of and how they interact with the atmosphere? Is that an important component of the research?
Well, I think the biggest missing piece of knowledge is the particulars of a given asteroid. So I do think we have a good understanding of the process of reentry, or entry in this case, ablation, the physics of the ionization processes, and how, you know, how the asteroidal material is vaporizing and how it's fragmenting. But without the details of the structure of the asteroid, there's a lot of uncertainty in the initial conditions. What is it that's coming at you if you don't know in excruciating detail what it is that's coming at you? It's very difficult to predict in such a nonlinear, chaotic system.
And in fact, all the space missions that are planned or that have visited or made a flyby of an asteroid, none of them carries an instrument to probe the internal structure. So all we say about the internal structure of asteroids relies on our interpretation based on surface morphology, bulk density of the asteroid when it is measured, modeling, but we don't have any direct information. And therefore, even when we say an asteroid is an aggregate which was formed by reaccumulation after a disruption, what do we mean by that? what are the pieces? Are there big blocks with big voids separating them, or is it more like small grains all together? You could have exactly the same body with totally different internal structure. And this has a very big consequence, because the response to an impact of an asteroid, if we talk about the kinetic impactor, highly depend on the internal structure, because the shock wave, the way the shock wave will go through the asteroid depends whether it would encounter voids, whether there will be fractures, etc. And we don't have any direct knowledge on
The
that.
important thing to remember is that, as well, that we cannot get that information from Earth-based telescopes. It's impossible. To do that, you really need space missions.
And from a planetary defense point of view, Brian, we're really never going to have that information, that privilege of having that time to really understand precisely what it is, and we're going to have to make a conservative assumption that it's sort of the worst case coming at us and evacuate a large enough area to save as many lives as possible.
Well, thank you. We've run out of time again, but you certainly characterised the problem as difficult, I think. So thank you very much. Over to Sabinia.
Thank you, Brian and gentlemen. And even though you've characterized the problem as difficult, I hope that you viewers are finding all of this knowledge easy to digest, and it's making you just a little bit smarter or a little bit more curious about asteroids. And I'd like to go over to Asteroid Day in Spain and Joseph Rodriguez, who I hope will brief us a bit about their laboratory experiments to understand the physical properties of hazardous asteroids. So Joseph, welcome.
Thank you very much. Yes, here at the Upper Research Council, we are doing experiments to understand how these meteorites behave, and because these meteorites that are reaching the Earth are pieces of asteroids, and then our laboratory samples that reach the surface of the Earth to allow us to understand the mechanical properties and the bulk chemistry of this asteroid. So it's just a step forward in understanding how they behave and how we can, for example, deflect them by using a kinetic impactor. We are full supporters of the Asteroid Impact Mission and the AIDA, together with the NASA mission, DART. And in particular, from Spain and in Catalonia in particular, we have been big supporters of the Asteroid Day. We have in hands what was the first book of the event that took up in Barcelona in 2015. Was the first year we celebrate, and we are really happy to be here. We congratulate to all the organizers over the world, because we are getting big. We also thank the United Nations for this support to the initiative. And for this year, we have events in Madrid, Mallorca, Castelló, Terrassa, all over Spain. In 2 hours, in fact, I myself live in the Asteroid Day, Colombia, and in 5 hours, an important outreach talk also in Terrassa, in Barcelona.
Thank you so much, Joseph.
Thank you very much.
Thank you, and thank you for your support, Asteroid Day Spain. And we've talked about that Asteroid Day is about raising awareness and about education. So I think it's a perfect opportunity to now hand over to the University of Austria, where I have Mattia Gallazio, who will share some insights. Hi, Mattia.
Hello, Mattia Gallazio. Hello, everybody from the Department of Astrophysics of Vienna. We are very happy to host the Asteroid Day also here. We will show to the Viennese people asteroids in all their aspects, and about impact, physical characteristic, their orbits. We also show them asteroids from amateurs via telescopes. Maybe tonight, if it is good weather, we can see Juno. And we will show about all the refractor. And we made also an asteroid cinema for the children and the families.
Okay, thank you very much, and thank you, and happy Asteroid Day.
Welcome, happy to you, to everyone.
Thank you. And now it's time to head over to Natalie, who's at the Science Center, and this time she's in the experimental room. Over to you, Natalie.
Yes, hello, welcome back. And I am very, very honored to have with me two astronauts, and it's Nicole Stott and Doreen Prenario. And as you can see, I'm not alone. I'm here with students from ICE School, all Luxembourgish students who are here today to have a look at the Science Center. Nicole, you are an American NASA astronaut. You flew on the space shuttles Atlantis and Discovery. You lived and worked for over 100 days on the ISS. Formerly, most astronauts came from the military sphere. But you say that all the different jobs you had at NASA really prepared you well for being an astronaut.
I had the opportunity to work for 10, 11 years at the Kennedy Space Center and the Johnson Space Center on the shuttle program. And I mean, up close and personal with the hardware and the people that took care and built and maintained the space shuttle, and then also the space station. And so that experience, that hands-on kind of intimate time with the hardware and the people that took care of it was very, very helpful in preparing to fly on those spaceships.
You are known today as the artistic astronaut. You were actually the first astronaut to paint in space. When did you discover that passion?
Well, all growing up, I loved artsy, craftsy things my entire life. And when I was told that I could take up some personal items for my free time in space, a paint set, a little watercolor kit was what I decided to take with me. And I had the opportunity to paint something that I had taken a picture of through the window. It was really special.
Now, as an astronaut, are you more sensitive to environmental issues? Because one of the missions of the Association of Space Explorers is to foster the stewardship of our home planet.
Absolutely, and I think you'll hear all of us speak to our planet as Spaceship Earth. I mean, we believe that we are all crew, not just passengers on this planet, and it is our obligation to take care of it so that we can continue to survive here. And definitely that view from space, that glowing, colorful view of our planet, just reinforces that obligation, I think, that we are responsible for where we live.
Doreen, you are the first and only Romanian astronaut. You are former president of the Romanian Space Agency. You are the founding member of the Association of Space Explorers. Can you tell us a little bit more about the main missions of that association?
Yes, right. The Association of Space Explorers was organized in 1985. 25 astronauts and cosmonauts were gathered from 13 countries to decide what to do together to improve the knowledge of the people about the Earth, about the protection of the Earth, and how to manage the professional problems that we face into the outer space. And we organized the Association of Space Explorers. The main goal is to provide a professional forum between us to discuss professional problems, but in the same time to promote the education of the young generation, to understand much better the world, to understand science, to approach the science, and to have a future generation of scientists to work for space. So we are aware that our activity have to be continued by very wise and well-educated people.
Mm-hmm. And you are also very happy with the work that you have at the UN and that you do together with the UN. Why?
Yes, I started to work within the UN Committee on the Peaceful Uses of Outer Space in 1992. So very long time ago. In 1993, I promoted a little bit the idea that our Association of Space Explorers become an observer member of the UN. And next year, it became an observer member. From that time, I'm very much involved on behalf of my country and on behalf of the Association of Space Explorers with all problems debated at the level of the UN. And one of the main problems is the near-Earth objects. I mean the asteroids and comets that could pose a hazard to our Earth. And I'm very happy that I could contribute very hardly to the promotion of the Asteroid Day as well, because on behalf of the Association of Space Explorers, last year I proposed to the UN Committee on the Peaceful Uses of Outer Space to promote the idea at the level of the General Assembly to recognize the Asteroid Day as an international event, international movement to promote the knowledge and information for the general public about asteroids.
Yeah, and I think it's also great that 105 astronauts work today with the Asteroid Day. So happy Asteroid Day, and back to you to the studio.
And we are back here, so we are still looking up, looking for asteroids. But now I would like to show you some images I took personally about near-Earth asteroids. With this telescope, part of the Virtual Telescope project. We are not using it right now because it is in Italy just in broad daylight. But I would like to show you some images we took, and especially with a very special citation. This is the asteroid Freddie Mercury. You remember when Brian May presented this to the world last year. So I just wanted to show this image about this important asteroid, of course. But back to near-Earth objects. Here it is, an asteroid we tracked a few weeks ago. It was 2017 GM. This one arrived more or less 16,000 kilometers from the Earth's surface. So quite close. It was very small, but very interesting case, I must say. This one is very special for me. It showed up in the sky late last year. It was 1st of November. It was 2016 VA. And I want to show you here how the asteroid is looking like a dot of light while the stars are trailing, because our telescope is really able to track at any apparent rate, any rock up there. We can really follow it very well. And this is something very special, friends, because here you will see something very rare. It is the same asteroid traveling close to us, and it is now disappearing because it just entered the shadow of the Earth. This is an eclipse over the asteroid. It was great that we could predict this and be ready to cover this. It is quite rare to see this kind of animation. So happy to be here at Asteroid Day sharing this with you. Going again, just a couple of animations still showing asteroids moving all around. You may be impressed to see how fast they look moving up, but of course this speed is somewhat accelerated just for, for more efficiency for our public. They are not moving so fast, but they are not joking after all. Here it is perhaps one of the most famous asteroid ever. Its close approach was scheduled the very same day of the Chelyabinsk event. It was 2012 DA14, and that evening we tracked this among clouds. And I'm happy and proud that we were able to track this, and the very same moment it was closer than the geostationary satellite. So very critical and very, I must say, very hard to follow object. And just to conclude, this is what you can do when you track the luminosity of an asteroid over the time. You can see a dot of light visually, but you can reveal the physical shape of the object while it rotates. So this is a very nice technique just to go and discover the phase of the asteroid. So I want to thank you again, and let's go and see what Stuart has for us.
Thanks, Gianluca. I'm joined now by Marcus Peyer, who's Vice President of Corporate Communications and PR at SES. And SES are one of our generous sponsors that makes Asteroid Day possible. Marcus, welcome.
Thank you.
And tell us a little bit about SES and why the interest in Asteroid Day.
It's all about good citizenship and connectivity. Good citizenship in the sense that we are a space citizen. We inhabit space since decades. With our large fleet of 66 satellites, we are running one of the largest infrastructures out in space on a day-to-day basis and have expertise and knowledge and competence. Second, it is also about being a Luxembourgish citizen, because all the activities that Luxembourg develops in space very successfully, as you can see with SES, are of course part of our thinking. We play our role in it. We support the space cluster and its development. And we like to think like Luxembourg of asteroids also as a resource, not only a risk. Connectivity, because this signal of this very broadcast is on our fleet, and thanks to that, right now, can be viewed by millions of people around the world.
Yes, well, thank you so much for the use of your satellites and your interest in asteroids. We are going to come back in a few seconds now with a panel about how humanity fell in love with asteroids in the first place.